right, so let's look at the addition rule. And this is 5.2. All right, so two events are disjoint if they have no outcomes in common. They're also called mutually exclusive events. So disjoint and mutually exclusive are the same thing. All right, so the addition rule for disjoint events, if E and F are disjoint, then the probability of E or F occurring would just be the probability of E plus the probability of F. All right, so before I do this next example, let's look at deck of cards. Make sure everybody's clear. Some people don't play with cards. Let's go here, standard.
Some people don't play with a full deck of cards.
Had to get that one in there, didn't you?
You just made it so easy for me.
Uh, um. All right, so deck of cards, standard 52 card deck. So the reason why they say standard, in other words, that means no jokers. No jokers are in there. So should be four suits, spades, clubs, diamonds, and hearts. Two black suits, spades and clubs. Two red suits, diamonds and hearts. 13 cards each suit. So it'll be three face cards and 10 regular cards. And we talk about regular in terms of face or not having a face because, of course, the ace is not a regular card as far as value is concerned, but it does not have a face. So your three face cards, king, queen, jacks. That's what jacks, just king, queen, jack. But and then your 10 regular cards, ace, and then the numbers 2 through 10. All right, questions on that before you do a problem using cards.
Nope.
All right.
Baby bomb.
All right, suppose a single card is selected from a standard 52 card deck. First, it wants to compute the probability of drawing a king, then compute the probability of drawing a king, queen, or jack. All right, let's look at A first. Now, our sample space, remember, we're always going to use S for our sample space, and that's 52. So don't forget the total number of possibilities. So that's what your sample space is, the total number of possibilities. Then we have our kings. So remember, each suit has a king, and there are 4 suits. So there should be 4 kings. All right, any problem so far? So, probability of getting a king is to take the 4, place it over 52. We can reduce that down to 1 over 13. Questions on that?
Sir, what is the N?
Just the number of. So the number of cards in the sample space is 52. Number of cards in the king, number of kings that we have will be 4.
Got you.
Mm-hmm.
Thank you.
Nope, no problem, no problem. All right. So B wants to find the probability of drawing a king, queen, or jack. Now, one thing we need to establish or make sure we're okay with the idea is that these events are mutually exclusive. Or in other words, disjoint, remember disjoint and mutually exclusive are the same thing. They do not have any cards in common. All right. Sorry, I couldn't get my. Yeah, for some reason I couldn't. It went muted and wouldn't let me unmute. All right, so the events are mutually exclusive, or in other words, disjoint. They do not have any cards in common. So that means we can just find the probability of each event and add them together. All right. So we already done king, but I'm just gonna.
Wouldn't it be the same for the hearts, the diamonds, and the spades? The same 1 out of 13, 1 over 13?
What do you mean? It would be the same for the king, queen, and jack. Yeah.
Yeah, that's what I meant.
Yeah. Yep. Gonna be the same for all 3. But I'm just gonna go through the process just in case you don't get one that it would be the same for.
Thank you.
Yep. No problem. So in each one of them, if I could write the right letter, you would establish the sample space, establish the number of outcomes in the event, and then put the number of that event over the sample space. Same thing here for queen. Number in your sample space is 52. Number of queens in the deck is 4. So the probability of getting a queen is 452. Number of cards, 52. Number of jacks, 4. And the probability of getting a jack is 452. Mm-hmm. Yeah, okay, let's do this. Probably get a king or queen or jack. King, jack. And this will reduce down to 3/13. All right. So questions on anything before we go any further?
Nope. Nope.
Mhm. Hmm. I'll do it like that. All right, problem before I scroll all the way up. Everybody good? All right. So a single die is tossed. Find the probability of rolling a number less than 3 or greater than 3. So when we look at a die, a single die, and we talked about this already, your options for your single die. So your sample space, number of your sample space is just 6. So you're talking about less than 3. So I can call it L. Less than 3 are the values 1 and 2. So the number of elements, and there's 2. So the probability of getting a value less than 3 would be 2/6. Remember using this as our sample space.
Do you reduce that?
Nah, we can leave it like that first. I'll show you why in a second, why we can leave it that way. We'll reduce it at the end though. So greater than 3, I can call that G. Talking about 4, 5, 6. So the number of elements in this event would be 3. And the probability of getting this would be 3/6. So now the reason why I will hold off reducing this, because when I reduce this, it's going to be 1/3. When I reduce this, it's going to be 1/2. I'm going to add these fractions together. So when I add these together, I'm going to have to get common denominators, which is going to take them back to those fractions right there. So I would just go ahead and reduce at the end, and that'll save some work.
Okay.
So we want to know the probability of getting less than 3 or greater than 3. So we'll add the probability of less than and the probability of greater than together. So it's 2 over 6 plus 3 over 6. Answer would be 5 over 6.
Easy peasy.
All right, so I didn't make enough room. All right, so here's our general addition rule. Remember the one we had before was for mutually exclusive events. This is just the general rule for any event that you come across. So the probability of E or F occurring will be the probability of E plus the probability of F minus the probability of E and F. So once again, E and F are not mutually exclusive, not necessarily mutually exclusive. This piece back here that we're subtracting, E and F, represents what E and F have in common. So if we did have mutually exclusive events, what they had in common would be 0, and that's why the additional rule for mutually exclusive events is just P, the probability of E plus the probability of F. So like I said, if they do have something in common, we have to subtract that. And so I will show you why that occurs. Single die, let's go back to dice. All right, so a single dice toss, find the probability of rolling an even number or a number less than 5. All right, so we look at even number first. Well, no, let's do this first. Sample space, even though we already know it from the last problem. Should always make a habit of establishing your sample space first. And that is 6 fourths, because we know it's numbers 1 through 6. Now we look at even number. So our even numbers, 2, 4, 6. So the number of even numbers is 3. And the probability of getting an even number is 3 out of 6. All right. Number less than 5. We can call that L. Numbers less than 5, 1, 2, 3, and 4. Number of elements in this event would be 4. Probability of that occurring would be 4 out of 6. So before we go any further, make sure we're okay. Now, say again?
That doesn't reduce?
Nope, not yet. Like I said, we're gonna do that at the end.
Okay, you just doing the same thing. Got it.
Yeah, because and then like just to reemphasize why this would be 1/2, this would be 2/3. But when I add my fractions, I have to have a common denominator, so that means I would have to take it back to these fractions anyway.
Just eliminate that extra element.
Yep. So now, if we decide to add these at this moment, and this is not part of the process, so I'm just scratching here just to show you why this wouldn't work. 3 over 6 plus 4 over 6 would be 7 over 6. That would be more than 100% or more than 1. Remember, your probabilities cannot be greater than 1. So that means somewhere we either went wrong or somewhere we missed something. And so let's look at the fact that these two outcomes have something in common. Is it possible to be even and less than 5? The answer is yes. So let's call this E and L. And that would be 2 and 4, being even and less than 5. So the number of outcomes in even and L is 2. Probability of E and L is 2 over 6. So now, if we take note or go back to our general addition rule, know that we are going to subtract this piece right here, what they have in common. Reason being is because notice in our even setup, we have 2 and 4. And in our less than, we also have 2 and 4. So when we add those probabilities together, we're actually counting 2 and 4 twice. All right. When we add those probabilities together, we're actually counting 2 and 4 twice. Hold on 1 second. Let me make sure I got this right. Okay, yeah. That's what it's technology. Okay, so that's why we have to subtract it at least one time so we don't count it twice. And that will put my probability under 6. So probability of E or L probability of E plus probability of L minus E and L. 3, 6, 4, 6, 2, 6. And that will give me 5, 6. That's my final answer. Got a 5 out of 6 chance of getting an even number or a number less than 5. All right, so next one. Single card is drawn from standard 52 card deck. Compute. Do I? All right, so single card is drawn from the standard 50 card deck. Compute the probability of the event, should say of the events, of drawing a king or drawing a diamond. All right. And if you want to know initially whether you need to establish or whether you need to figure out if they have anything in common or not, or if you need that probability, you should look at it firsthand. Are events mutually exclusive? Answer is no. There is a king of diamonds that we have to give an account for. All right. And so let's look at each one of them individually first, just like before. All right, so we're looking at the king. So we know the sample space is 52. Number of kings in the deck is 4. Probability of getting a king is 4 out of 52. Diamonds, number of diamonds is 52. I said number of diamonds. Sample space is 52. Number of diamonds would be 13. It's 13 diamonds in the deck. And the probability of getting a diamond would be 13 out of 52. Then we're talking about being a king. And if I can write and, being a diamond. Number of king of diamonds would just be 1. There's only 1 king of diamonds. So the probability of getting a king and a diamond is 1 out of 52 chance. All right, so any problems with any of those numbers before we calculate with them? Let's see if I want to do another example. That should be fine. Okay, so finishing this off, probability of king or diamond. So that's the formula. If you want to know the probability of getting a king or a diamond, probability of king plus probability of diamond minus the probability of king and diamond. So that's 4 over 52, 13 over 52, minus 1 over 52. That'd be 16 over 52. And that can reduce. That's 4 times 4, 4 times 13. 4 is cancel. 4 over 13.
Good job.
Thank you, ma'am. Appreciate you. Questions? Any questions?
Nope.
All right, so your complement of an event will be all of the outcomes in the sample space that are not in the event. And we notate that with that event letter raised to the C, the superscript C. So E to the C would be the complement of the event E. So I want to say EC or just the complement of E. All right, so for the complement rule, just 3 different ways of representing that relationship. The probability of your complement is going to be 1 plus the probability of your event. Probability of your event is 1 plus the probability of your complement. And it also means the probability of your event plus the probability of your complement is going to equal to 1. So that's always the relationship between the event and its complement. All right. So according to the National Gambling Impact Study Commission, 52% of Americans have played state lotteries. What is the probability that a randomly selected American has not played a state lottery?
Do we have to know how many Americans there are total first?
Nope. Nope. Yeah, it's not even that deep for us.
Is it 48, sir?
Yep. Yep. That's all it is.
I don't know if we was doing percentages or what.
Yeah. We don't have to do it. So, really this would have been like, let's say if you wanted to convert to a decimal, would have been 52. I mean, a fraction would have been 52 over 100. So like those fractions that we've been getting, like let's say 2/3. If I want to know the percentage, I would convert it to a decimal, and then that would
So
be
it's a trick
56%.
question.
Mm-hmm. Say that again.
It's a trick question because see, I would have been trying to break down all the math.
Yeah, that's what I was saying.
I would have known right off the back that it was percentages. You just subtract 52% from 100%.
Yep, that's it. That's all you got to do. So, just in case it gets more wordy or something like that, so you establish what does the 52% represent. So those are the Americans. Let me just do it like this. Probability of people that played the lottery is 52%. Of course, that's 0.52. So the percentage of people that have not played, when I say people, I guess should say Americans, not necessarily just people. So if you want to find a percentage of people that has not played, you would just do 1 minus the 0.52, which is 0.58. I mean 58.48, and that'll be your answer. And my math lab will let you know if they want it in percentage or if you can leave it in decimal. Well, either one of those, it's good enough. Now we'll do more with the complement and the application of the complements later. That's the only real example. Let me see if they got another good example of using your complement. But yeah, so that's good. Your complement is always going to be 1 minus the event. So, and then your event will be 1 minus your complement. Let's see if I did put that. Oh, did I put 1 plus up here? Y'all let me put a plus right here.
No, you put a 1 plus.
Oh, and my pen won't erase it. All right, there we go.
Are you using an Apple Pen?
No, actually using the Surface. Yep, Surface Pro. So it comes with the pen. So yeah, y'all go back to that. I put a plus. It just hit me when I did the subtraction down here. I thought about it. I said, I don't remember putting a subtraction sign. Yeah, that should be 1 minus your probability in each case. And then the plus is right here when you add them together.
Sir, what's the EC? The C, is that squared?
No, that's just notation for the complement of your event.
Okay.
Yep. So let's go back. Let's say if I go to when we were talking about kings, and I said the probability of getting a king was 4 out of 52, which was 1 out of 13. Now, if I want to know the complement of getting a king, so that's everything else.
Oh,
You would just do, yeah, that little C notation lets you know that. And so what you would do is just do 1 minus 1/13, and that would be 12/13.
thank you.
So yeah, no problem, no problem. All right. Let's see. That's it for 5-2. Y'all want to do 5-3? Anybody excited about doing 5-3?
Might as well.
Let's see. 5-3. I think this chapter goes to 5. Let me check. No, it goes to 5-4. Yeah, 5-4. So we can start 5-3 and then finish it with 5-4 next class. All right, so independence and the multiplication rule. All right, so two events are independent if the occurrence of one event does not affect the other. And then two events are dependent if the occurrence of one event does affect the other. I think independence and yeah, dependence is the next section. So this section we'll talk about independence more so than the dependence. I should have said are the events. Do that right here. All right. So suppose you flip a coin and roll a die. Are the events obtain a head and roll a 5 independent? All right. So yes, they are independent. One has nothing to do with the other. So one is flipping a coin, the other one is rolling a die. Neither one of them changes the probability of the other one occurring. Just earn. All right, so the next one are the events earned a bachelor's degree and earn more than $100,000 per year independent,
No.
right? They are not independent. Um, so they are not independent because earning a bachelor's degree increases your chance of earning $100,000. Of course, it doesn't guarantee that you will, but it does increase your chance of earning $100,000.
You know this had to be written a long time ago. Bachelor's degree now might earn you minimum wage.
Yeah, it has gone down a little. What time is it? I want to make sure I get to. So yeah, I don't have to do another. That's good enough. Let's do an actual problem. All right, so the multiplication rule for independent events, E and F are considered independent. So that is something you want to establish first. Are your events independent? Because if they are dependent, then we'll have to do something else. That's in next section. But we have to make sure that our events are independent so we can use this with no problem. So if E and F are independent, then we would just multiply your probabilities together. All right. So if we want to know the probability of E and F, remember last time we were looking at E or F occurring. That's why we did the addition. This time we're looking at E and F happening. So not either or. We want both of them to occur. What's the probability of both of them occurring? Mess this all up. All right, so in the game roulette, the wheel has slots numbered 0, 00, and 1 through 36. A metal ball rolls around a wheel until it falls into one of the numbered slots. What is the probability that the ball will land in the slot numbered 17 two times in a row? All right. So first thing we need to establish and make sure we're cool with the idea of dependence or independence. So these events are independent. Um, the occurrence of hitting, what would say, rolling 17 does not affect So these events are independent. The occurrence of rolling a 17 does not affect rolling a 17 again. So it's not like if you were to roll 17, then they block off a number or they block off 17 so that you can't roll it or maybe something weird. No, they take the ball up and then you roll again. So the probability is still the same for each opportunity when you go to roll. So the events are independent. If that's the case, we use our independent multiplication rule for independent events. First thing we need to do is establish our sample space. Now the number of our sample space, if we go back, remember this is the total number of possible outcomes. We have 0, double 0, and 1 through 36. So that is, or that would be 38 possible outcomes for us. All right. And then the number of 17s on the wheel is just 1. So the probability of getting a 17 is 1 over 38. All right. So the probability of getting a 17 and then 17 again. I'm going to go down here where I have more room. And just take the probability of each one of them. Multiply them together. It's 1 over 1. Yep. And that is approximately 0.0006925. And once again, and I'm giving you that number because I saw it in the example, but my math lab will let you know which one to use. Both of them are fine. Any questions? Questions? All right, so we got 6 minutes. So we have 2 examples that I want to do together that's left out of this section. So we'll stop right here. I don't want to run out of time. Do one now, then do one next class. So we'll pick up right here on next class, finish off 5-3 and then knock out 5-4. So before we close out, any questions, concerns, comments? Is everybody good?
Yep. Nope. Nope. And yep. No questions. And yep, I'm good.
All right, sounds good.
Mr. Tucker?
Yes.
So I emailed you the assignment 1 and 2.
Okay.
Yeah.
All right. So when did you shoot that email to me?
I shot it to you like 10:30, like 10, about 10:45 this morning.
Oh, okay. Yeah, I haven't checked my emails this morning, so I'll get to it. I'll probably do it right when I can have a break after this class. So I'll check it out.
Okay, thank you.
All right. Thank you. Appreciate that. All right. So if you guys are good, I'm good.
Wait, I do have a question.
Yes.
That test on chapters, what was it? Chapter 1 and 2? Whatever. When is that due?
Right now I don't have a due date, so just as soon as possible.
Okay, good. Okay, work on it today. I was up till 4:30 doing my work.
Okay, so you had a good time.
No, it sounds like I don't have a life.
So, all right. Well, you guys take care. Have a good one. I'll see you on Thursday.
All right, you too.
All right.
Thank you.
All right. Thank you.